SwayamPrabha. Digital India. Educated India.
So, this small section, in this small section we are going to briefly demonstrate some sheet forming experiment. These experiments were done in some of our labs with a very simple setup, which will be easy for anybody to do it in their labs, and we can evaluate certain outputs from that. So, the first one, the video will be there, you can look into this. This is the V bending of sheet. Initially sheet was shown, and here you can see a setup we have with a simple punch. So, this is your actually the punch. Okay, it is a V bending punch, and this is the die. You can see the channel here, which is of V shape, and if you look into this punch here, this particular punch, okay, can be replaced, and there is a fastener above that. You can see here this fastener can be removed and the punch can be replaced, so that you can make a different dimensions of punch with a different corner radius maybe, and you can see that the person is showing that you have to keep it like this, and the punch will be clamped in the machine now. Die will also be clamped, you will see. Yes, so the clamping is done. You can see a simple setup here. Okay, it is simple to easy to install it in an UTM. This is a simple hydraulic UTM, you can see, and the punch is actually tightened. This punch can be replaced. You can see that there is a T slot which is used to clamp the punch, and which can be replaced. You can install a new punch with that, and the punch is adjusted, you can see. Yes, so and you will see that now this die is kept on the UTM. So, this setup is little heavy, okay, so that you may not need to actually clamp the tool, rather you can just keep it. It can lie on a place with its own weight. So, but only thing is you have to adjust it in such that when the punch comes down, it should match with the groove. So, you can see that slowly the punch is giving vertical displacement, the ram is coming down. So, the hydraulic is adjusted, you can see. And the punch is coming down, and slowly, because it is a screw driven, so it is coming down slowly, and once it reaches the die level, then you have to be careful, you have to little bit adjust it, so that the punch is in line with the channel, V channel or V groove. So, it is nearing the die position, and we may have to locate the sheet properly here, and you can just see that yeah, so you have to just check whether it is reached that level or not. Okay, once it is reached, you can remove the sheet, and you can just see now that it will be adjusted. So, it has come down, and then you have to adjust it. So, the final one should be clamped properly. Until then you have to little bit adjust it, so that So, now it is adjusted. So, after this die should not be moved. So, you have to be little bit careful, die should not be moved after this. Yes, now it is moved up, it is located properly. And now the sheet is kept located on the die. We are not going to use any lubricant or anything in this. It is a simple bending operation, V bending operation, and you will see that here there is no holding. So, it is just moment, only sheet moment is given to the sheet for it to bend. So, there is no applied tension here. So, you are going to give only moment to that. And you will see that now vertical displacement is given to the ram, and punch is also moving down, the sheet is bending. The sheet is further bent. So, now you have to bend the sheet to such an extent that it takes almost the shape of the this V groove. So, you can see that on the die surface the sheet is moving up, right. So, which means that it is not held in that location, it is just bending with moment. So, it is bent. So, now depending on this angle it may little bit slide in, and the important point that one should look right now is after a particular stage, the displacement will be stopped and the ram will be taken away. At that time you will see that the sheet will try to relax. You can see spring back, it will try to relax. The angle is going to change now, you can see. So, it has gone down, and maybe even if you stop it now, and if you try to displace in the upward direction, slowly you will see some relaxation. You see that it is relaxed now. So, the sheet is relaxing, you see that the angle, included angle is now, which is not the same as that of the die, it has increased now. And now it's like experiment is over now. So, you can take the sheet out and the sheet is bent. This must be some aluminum alloy, the sheet must be an aluminum alloy, and you can see whether is there any necking happened on the outside region. Okay. On the tensile surface you can see on the bottom one, yeah. So, there is no neck, no crack is developed, it is still fine. Okay. But you can measure the included angle and you can compare it with the die angle. So, you can get some idea of what is the spring back, the angle change. So, like this one can compare materials of different strength and ductility to check how bending happens. So, this is a simple V bending setup which you can make it in a lab itself, and you can do this kind of experiments. Theoretically we did some analysis to evaluate spring back and to evaluate you can also get load displacement graph from the machine itself. Okay. There will be a computer interface. The next experiment we will see, in different experiment there will be a computer interface, in that you can get load displacement graph which will give you some idea of what kind of load it is going to have during deformation. So, this is about your V bending of sheet, and simple tools are there. One die is required and there is a corresponding punch that is required. So, punch can be replaced. So, you can change the punch corner radius to see is there any change in the deformation in spring back. All those studies can be made. Okay. So, you can also do some materials processing on the sheet to change the deformation pattern. Say for example, you can do some sort of heat treatment, you can do some processing like friction stir processing, and you can study the bending behavior. These are all possible now. Let us go to the next one, which is on deep drawing. So, you will see that here This is the blank holder, the first one which is shown, which has got lot of holes there to clamp it onto the die, and this is the die. The central hole is actually the die hole, okay, into which the sheet is going to be pushed inside. Okay, the inward movement will happen, radial movement will happen inside that, and the column which is shown, which is just below that ring region, is actually will be used to clamp the die onto the machine. And there are two windows on this vertical column, you can see here. Okay, here also you can see some. So, with that can be used to see whether the sheet is actually drawing in or not, or you want to check something, you can do that. You can put a camera inside and you can just see the deformation level if you want to. So, again this is a bit heavy setup, but then you can make it with simple hardwares in your lab itself. This must be a, I think, a stainless steel sheet which must be having good deep drawability, and you can apply little lubricant on that, which is what is shown here. You can see lot of fasteners are there, align key, spanners are required. So, it is a simple setup. There is a blank holder and there is a die. So, and you can apply on the die surface. So, the sheet diameter is taken such a way that it is diameter is less than the location where fastening is going to happen. So, I am just going to place a sheet here, right. So, it is placed coaxially, okay, it should be at exactly at the center, but one difficulty in this, we cannot see the deformation. So, the sheet can slide in, it may not be axisymmetric while it is deforming. So, one has to be careful. So, you are going to place a blank holder like a ring. So, here blank holding is done with mechanical fastening, okay. Instead of hydraulic gripping, here you are going to do mechanical fastening, and you can put fasteners like this and you can tighten it. So, you can give a full tightening so that you have some blank holding force on the sheet, so that it can avoid wrinkling. So, there are probably 8 fasteners required. So, all may not be required, maybe you can have maybe 4 also would be sufficient. So, the cup that will be formed in this will have about 50 mm diameter, okay. So, accordingly the setup has been made. So, now the second fastener is tightened. The fastener can be kept upside down also, so that there is no disturbance for the punch movement in the vertical direction. So, the third fastener is located now. So, while doing it, one should be very careful that the sheet is not displaced from its position, that is very important. So, if you, so this is just a demonstration class. So, if you are going to do some experiments which will be useful for your project, research work type of thing, where data is very important for you, practical data, and you want to verify it with some theoretical calculations, estimation, then you have to do it meticulously. You have to check couple of times whether the sheet is displaced after locking all these things, or after locking it should not get displaced, or while locking it should not get displaced. One should look into all these things. The steps are very important here, and you have also put lubricant. So, there are chances that it may slide from its position. So, one should be careful. So, and you can see that the entire setup is going to be clamped in the same machine. We have used a simple machine UTM, but this can also be installed in a dynamic testing machine as well, so wherein you can get accurate data, and you can see the punch is already installed onto the upper ram, okay. The punch is already installed, you can see that this fellow, okay, is already installed into the upper ram. It is a cylindrical punch, okay, which is going to match with the die hole. It is a simple setup. So, and like in the V bending operations, here also you have to locate your punch appropriately, so that you have to adjust the die and then you have to clamp the die. And now you allow vertical displacement by using your machine. You can see that it is a UTM and the hydraulic can be controlled, and there is a computer interface on your right, okay. So, and all the details can be mentioned here. Okay, and when you start the test, because of vertical movement, your sheet will be pushed inside the die hole because of radial inward movement on the die surface. Yeah, so now the test is started, I think, and you will see the load displacement graph can be obtained like this. So, you can start the machine and you can open hydraulic, so that deformation happens at a normal rate, slow rate, slowly. So, now yes, you can see that some data we are obtaining, load versus displacement, some data we are having. You can see that the load keeps on increasing with respect to displacement, about 1.5 mm, 1.6 mm displacement has been done now, which is about 9 kilonewton is going to reach. Okay. So, you can look into it, and then now I think the test is almost done now. So, it will take only maybe few minutes one can complete it. So, you can remove the punch, take it out and take the entire setup, unlock it and take the entire setup out. Yes, and then unlock your blank holding ring, blank holder ring, and you can see that a cup is formed, but here you can see that actually the sheet is little bit displaced and the cup is not axisymmetric. You can see if some flange region is there on one side and flange region is totally gone on the other side. You can see that. That is why I was telling you that you have to be very, very careful when you do this. If you want to take real data which will be useful for some calculations, then you have to locate it properly. So, this is how cup is formed, and you can see in this final cup there is some small waviness in the wall region. Okay. Wherever you have the cup that is fully drawn on the left side, you can see there is small wrinkling on the walls, that should not be there. Okay. And one good thing is that there is no wrinkling on the flange region which you can which is visible. Okay. And one can get a full load displacement graph and you can do any analysis you want, or you can do you can validate it with experimental results if you have some analytical modeling done. So, in the previous video we have seen deep drawing of sheet. Now, I am going to show you another demonstration of same deep drawing, okay, to get an axisymmetric cup. In the previous one it was not axisymmetric, isn't it? So, I am just going to show you a demonstration. So, for same deep drawing, and you will see that again the same die is used. Okay, I am just you will see that it is the same die. I am little fast forwarding it. Okay, and it is a 50 mm cup that is formed. So now you will see that the sheet will be it's a circular sheet. The same sheet is taken. So, if you want to measure strains on the sheet surface, then you may have to put circle grids on that. You may have to print circle grids so that you can measure strains at different locations of the deep drawn cup. So, you have a flange region, cup wall and cup bottom like that. So, you put lubricant so that you have some nice cup that is formed. Grease would be better, and you need to put fasteners also. So, you place it, it should be symmetric, otherwise you will get a distorted cup. So, you have to locate it properly. See, moment you put lubricant, you have to be careful. Yeah. So what you do is either you can keep the die on the machine, and then you can place the sheet and blank holder, all those things, or you can arrange everything outside and then place the die entire assembled setup on the machine. Both ways you can do. Okay, but this way doing it assembly outside the machine is actually safe. Okay, so that you don't need to see whether RAM is moving or not. Of course, you stop the machine and do, but then this is the safest way to do. So, you are putting fasteners, and it should be tightened such that appropriate blank holding force is given mechanically. It is a mechanical blank holding force only, not the hydraulic one, and it has to be tightened well, and so you have to adjust it, and then you can see that all the fasteners are now assembled. Yes, and it has been put on the UTM, same UTM which I used for the previous experiment. Now this rigid punch is held on the upper platen, and you allow hydraulic to come down, but when you do it, you have to do it a little bit slowly, so that you can so that the punch and the die are coaxial, become coaxial. So when you try to insert the punch, you have to be a little bit careful so that they slide very nicely. Yes, and then you can tighten the dies so that it does not get displaced. So now once your assembly is done in the machine, you can see you can start the displacement of the ram, and punch will move down, so that the cup is actually pushed inside the die hole to form the cup. Okay. And you can see that so this is your graphic interface. You can see load versus displacement, hydraulic is controlled, and you can see that y axis is load, x axis is displacement, and you can see the data. And we know that there will be a typical load displacement graph for any material, and you can see that it is continuing now. So load keeps on increasing, you will see that it goes on. Okay. So there is about 3.5 mm displacement, and load is about you have about 14 to 15 kilonewton is there. Okay. So you continue that until you get a full cup. Okay. So now only issue here is, so you may have to fabricate a setup through which you can see the cup that is formed. Okay. There are several ways to do. Okay. One way is you can make a window just below the die so that you can see it, or you can have a video, a camera sensor type of thing arrangement which can be kept below the the cup that is formed, and you can see in your computer or in mobile also, you can see whether it is drawn fully or not. There are several ways one can do it. So otherwise you have to get a sense from your load displacement graph. Okay. So that is the only way otherwise. So visual thing, you may have to make a separate camera arrangement for that. See, it is almost like 8 mm displacement, 8 mm cup height is formed now, and depending on the material and thickness, you will get the load. Okay. So otherwise it will keep on increasing. So we are just basically repeating the experiment, and it is going to be like this. So we keep on increasing it. So you can see the slope is slightly changed. So it is, you can see that it is almost saturating now, which means that there are chances of cup is already formed, because there is less material to get deformed. You can see that load is coming down actually. So you have to be a little bit careful. You can stop the machine. Yes. Stop the ram movement, and you may have to take it out slowly and then disassemble the setup, and you will see that this time at least let us see a nice circular cup is formed, which looks like an axisymmetric one. Yes, this is better than the previous one. You can see there is a small flange. We did not draw it fully so that you can see what is the status. There is a cup bottom that is formed, isn't it? There is a cup bottom is there. Okay, and you have a you have a flange region. So you can see that this is your flange region. Okay, and you have a cup bottom, and there is a cup wall region. So all three regions are formed, and now the cup is almost axisymmetric. So this is the way deep drawing has to be done. Okay, so now the next video which I am going to show you is basically you can see it is nothing but a stretch forming of sheets. So in the stretch forming of sheet, Okay. You will see that the main aim here is to basically deform the sheet, okay, and then through a punch, an experimental setup, punch, die, blank holder setup, and then deform the sheet so that at the end of the experiment you can actually construct a forming limit curve. That is the whole idea. Okay. So, we are not going to do deep drawing, rather what we are going to do is a stretching operation where the sheet is actually not going to draw in. That is the whole idea here. And as I told you previously, you want to measure strains on the sheet surface, which is mandatory, okay, when you construct a forming limit curve, because forming limit curve is between major strain and minor strain that we already studied. So, you want to get the necking strains or fracture strains, then you need to put circle grids on the surface. A simpler way to do it is through electrochemical etching. You can see that the person is doing electrochemical etching. This is the setup, and you can see that okay, it is nicely formed. Okay, you can see the circle grids are printed on the sheet surface, right, very nice ones are made. So, circle grids are particular diameter, one should know the diameter, initial diameter. Now, this is another sheet with a different strain path. And as you know, for evaluating this forming limit curve, okay, through this kind of stretching operations, limiting dome height test is generally followed. Okay, limiting dome height test is generally followed. We have elaborately discussed about it in one of the chapters. This is just a demonstration, and in this case you will know that there are several strain paths to which the material has to be deformed. The first one that was deformed is like for example in the negative minor strain, in the negative minor strain of the forming limit diagram. Okay, that is why you have width which is like of the order of 20 mm or something. But here the one which is now printed is in the plane strain path. That is why width is slightly larger. You can see at the mid region the width is slightly larger than the previous sheet, right. Here also circle grids are formed, you see that. So, you have to put the circle grids on the outer surface of the sheet when it is kept on the die punch setup, that you will see later on in this video. Now, this is the third strain path. So, I am going to show you only 3 strain paths. Okay. So, this is the third one. This is a circular sheet, you can see. So, this if you deform the sheet, this will deform in balanced biaxial stretching, okay, where alpha is equal to beta is equal to 1. The previous one is basically beta is equal to 0, okay. And you also know what it is going to be there for negative minor strain, for tensile strain path. And here you will see that the circle grids are made at the center of the sample. You can put for the whole sample, does not matter, because half of the sample will be in the clamping zone. So, it is not going to deform. Okay, so here nicely you see that the circle grid is formed here, you see. So, this stencil you have to make, the circle grid stencil, the green color one, that layer plastic sheet, you can make it. Okay, and this electrochemical setup can be, etching setup can be made. It is available in practice. Okay. So, this is a hydraulic press which we are going to use. This 100-ton hydraulic press which we are going to use for stretching operation, and you will see that the bottom one is basically you can see the die, and there is a projection, there is a draw bead, and punch is coming out, you can see punch will come from bottom. The uppermost one is actually the blank holder. Okay. So, there are 2 actions here. Okay. One, the blank holder will come and hold the sheet, and then inside that your die, punch will come from bottom. Okay. See, now this is the main difference between deep drawing and stretching with respect to the usage of machine. So, in deep drawing operation you will see the sheet is mechanically clamped with fasteners, right. So, but here you can see the sheet is clamped with a hydraulic pressure. So, its first action is done. Now, second action is nothing but a punch moving in the upward direction. So, naturally you cannot see that. Okay, the punch is deformed, the punch is moved up and it is deformed the sheet. You can see that. You have to deform it up to fracture. Okay. And of course, if you have ability to stop it at necking, that is good, because some materials undergo necking and then fracture. Okay. So, if you can stop it at necking, that is good, actually one should do that. But here is actually, since it is a demonstration, so it is actually fractured. Now, you see that circle grids are deformed into ellipses. So, you can find strains from that, right. So, you can find strains from that. near the fracture, and that becomes your your necking strains or limit strains of one particular strain path while developing the forming limit curve. So, you have to do like that for several strain paths, several alphas and betas, right. So, one is done, this is the second one, you can see this is second, this is for plain strain path. So, now it is clamped so that the sheet does not move in. Now, punch must be deforming the sheet. So, a deformation is going on. Yes, it is still going on, and you may have to fracture it, or you have to stop it at necking. So, now you can see that the sheet is again fractured. You can take it out now. You can see that the draw bead has created an impression. You can see that in the bend region, draw bead has created an impression, isn't it? That is why you need a draw bead, so that the sheet does not actually draw in actually. Okay, it is going to undergo only stretching. Now, you can see you can measure strain grids on the near the fracture location to get the limit strains in this particular strain path. Now, this is the third one. This is a third one, balanced biaxial stretching or equibiaxial stretching, you can say, or equibiaxial tension. Beta is equal to 1, alpha is equal to 1, no, that region it will come. So, now again it is clamping the sheet. So, you can adjust the blank holder pressure actually. Okay, you can adjust the blank holder pressure. If the sheet is not clamped well, you can easily find out, and on the left side of the machine there is a arrangement for increasing the blank holding pressure. So, once that is done, so your sheet will be clamped fully. And here also you can see that this is again fractured, but then it is too much of fracture. Okay. So, one should not go ahead like this actually, but you should be able to stop it just at fracture. One should try for that. We do that regularly. Okay. So, now here also you can see that the circle grids are deformed into ellipses. Okay. So, all the three sheets are deformed now, isn't it? So, now similarly you can have a few strain paths between the left and middle and right. So, basically you have to increase the width of the sheet, which is going to simulate some predefined strain paths. Okay. So, once that is done, you allow it to fracture, then you can measure the circle grids on the near the fracture location. That will give you the fracture strains near the to construct the forming limit curve. So, you know how to develop forming limit curve, which you already taught. So, all the fracture strains, major strain and minor strain, can be plotted in one graph, and then you have to draw a locus. Okay. And at several situations we have discussed how to evaluate major strain and minor strain, right. So, it is going to be pretty simple in the case of circle grids, because it is going to be converted into ellipses only, right. So, now here you will see that initial diameter is known to you, let us say 2.5 mm, and now the major axis dimension is measured, using microscope you can measure, and minor axis dimension is measured. So, from that you can get major strain and minor strain. So, you have to plot all this fracture data, fracture strains in one plot, okay, in one graph, okay, and then you draw a forming limit curve, okay, such that all the fracture strains are going to go above the curve. So, otherwise what you need to do is basically you need to measure the fracture strains near the fracture region, and you should also measure some safe strains away from the fracture region, okay, the region away from the fracture region. Say for example, couple of grids away from the fracture location. So, you plot all the strains in one graph and separate safe strains from fracture strains, okay, like the way we discussed in the actual lecture. Okay. So, that locus is nothing but your forming limit curve. Okay. So, if you plot it along with all the strains, so it is forming limit diagram. So, this way this limiting dome height test can be conducted, okay, in a hydraulic press, in which the sheet is clamped first, that is in the first action, and second action is punch is going to deform the sheet up to fracture. So, in deep drawing we have demonstrated that it can be done in a simple UTM, but here we have shown that this demonstration is done, stretching as demonstration is done in a hydraulic press. So, only difference is there in the UTM you need a mechanical clamping method, and here it is hydraulically clamped. Okay. So, this way one can develop forming limit curve, and you can do deep drawing, and previously we have also demonstrated about sheet bending operations. Tensile test, you know what to do, many of you have understood that. So, with this we stop this video demonstration. Thank you.